We're at Narrow Gauge in the Mammoth Hot Springs complex of Yellowstone National Park. Narrow Gauge is an exceptional environment to be able to study the interactions between microbes, water, and the precipitation of minerals, to be able to not only understand how rocks form as a result of microbial interaction, but also to study the complex mechanisms and interactions of evolution itself. Now, an important part of doing that is to be able to visualize or use photography and video work to see how microbes, water, and rock interact. Narrow Gauge and the rest of the Mammoth Hot Springs complex is really unique because the rate at which the minerals grow is about 10 to the 9th, 1 billion times faster than other natural environments on Earth. These include places like lakes and caves and rivers, other places where limestone, calcium carbonate, is formed relatively quickly. Here at Mammoth, the rates are an astronomical 1 billion times faster. In these same environments, in these same waters, we have microbes that love heat. And the description of that is a thermophile, a heat lover. Now, these microbes are primarily composed of bacteria, but we also have archaea, the methane-producing microbes. Now, that interaction between these together actually allows us to study how the process of mineralization takes place. Our studies at Mammoth over the years have shown that microbes in these waters, these thermophiles, actually produce a class of proteins in their cell walls as a result of them responding to the hot water and the flowing water. Now, at the same time, that protein actually allows the microbes to help drive the rate at which the minerals form even more quickly. And we call that process catalysis. So the catalysis via microbial proteins helps the rocks grow so fast here. Another natural process happening is the release of CO2. The waters here start on the gallatins, they go into the subsurface, they're heated, they react with marine limestones, and that process allows the waters to be supercharged with CO2 as well as other minerals that are required to make the travertine. So that combination of microbial protein catalysis and CO2 degassing makes everything happen super fast here. Now, that fast time frame is the segue for us to understand how biomineralization works. We are now running a series of experiments where a tripod is used to suspend a camera over the hot spring pools themselves. Now, in this location, the water's about a pH of 6.4 and a temperature of about 60. We're suspending a very high definition camera over the top of the location, primarily at the lips of these ponds' margins. Those are the environments in which some of the quickest growth rate occurs. And when I say quick, I mean 5 to 8 millimeters per day. 5 to 8 millimeters per day. That's how much rock is being deposited. And if you look at the system as a whole, that's happening every place in the Yellowstone complex. And that ends up producing about 25 to 30 to sometimes 50 tons of limestone being laid down a day in these spring systems. Now, this camera allows us then to track a process that happens very fast using time-lapse photography. In other words, the process of water, microbe, rock interaction is happening very fast. We have high-end cameras that allow us to take pictures of that process. In this case, it's every 15 seconds, so 4 frames per minute. Then we put together these individual photographs, stitch them together over long periods of time, and we get a movie. And that time-lapse movie then allows us to track specifically what the resulting growth rate is. That is a combination of being driven from microbial protein catalysis and CO2 degassing. Now, another thing about the morphologies here in the spring that we read before we put the experiments in the water is that these formations that make a step, we call them terracets. And to make the front edge of a terracet, you have to have the accumulation of limestone, it's called travertine, build up vertically. And for something to accumulate vertically, that means that it doesn't grow very much laterally, but it grows a lot just on the top surface. So we have a vertical growth and not very much lateral. The vertical growth in geology we call aggradation, and the horizontal growth in geology we call progradation. So by positioning small markers within the margins of these terracets and having those markers be both on the very top of the lip and also off the front face, then we can differentially quantitatively measure the growth rate. And again, at 5 to 8 millimeters per day, we can easily see on these small markers within the travertine how quickly and exactly what geometry and direction that growth accumulation is taking place. So A place like narrow gauge allows us to study this process called biomineralization. And that biomineralization, knowing the rates, knowing the ways it happens as a result of both physical and biological processes, allows us to take these results and apply them to a variety of things that are extremely important to our society, including pressing issues in energy, medicine, and even space exploration.